Hello everybody, my name is Wilke Trei and I'm going to introduce you today to the new BeamHash III proof of work scheme. So, welcome everybody to my living room. It had been a little bit strange time with all of the home office hours recently for all of us. But nevertheless, we had been busily working on the eager Electron update for Beam that's going to hit us all latest in July and will bring some long awaited feature, for example Lelantos or the confidential assets, and well, last but not least, also BeamHash 3. And this is what I'm going to introduce you today. What will be our new proof of work scheme? Where do we think it fits into the mining landscape? But also, what does it make better than BeamHash 2? Stay tuned. So, first of all, I want to show where we can find BeamHash 3 in the mining landscape. Well, let's build this landscape first. We of course start with the two big guys, SHA-256 and Equihash, the two famous proof of work of Bitcoin and Ethereum. By any means, definitely the most important proof of work schemes out there, because the networks are plainly the biggest you can find. Besides these two, also other proof of work schemes got a lot of attention recently. For example, the new Monero proof of work, that's RandomX, or also PoW, or its close sibling PoW, that's the new proof of work scheme behind Ravencoin. Well, but these are not the only proof of work schemes out there. There are many more. Let's, for example, add some that were initially CPU or GPU mineable, like Blake2B, SHA-3, well, some smaller Eagle Song, or the X family. What do I mean with X family? Well, most of you will remember X11 or X16 or X17. So these are all proof of work schemes that are originally composed of different other hash functions that are then melted into one single big hash function. What all of this here have in common is they are real hash functions in a sense. This is different from the next items I have here on my list. That is the Cuckoo family, that's currently used with Grin, or also Equihash 209, that's a proof of work scheme of Zcash. Equihash 209 is also the ancestor of all of the Equihash schemes that appeared later, and to those all of the BeamHash 3 proof of work schemes belong. Well, BeamHash 1, later than BeamHash 2, and now finally BeamHash 3. You see, the sorting here on my slide is not completely arbitrary. Instead, I kind of sorted them a bit on how much compute or memory heavy this proof of work schemes are. But additionally, also there's a rough sorting in how ASIC friendly or ASIC unfriendly they are. How easy or difficult is it to create an ASIC for this proof of work schemes. So well, you see I use the term of ASIC friendliness instead of ASIC resistancy, and well, that has a plain reason. I believe there are multiple different aspects you need to consider when talking about how friendly or unfriendly a proof of work scheme is for ASICs. In particular, I don't really believe it's possible to create a proof of work that cannot run on an ASIC. Instead, it will always be the case you are always able to create an ASIC by just taking the CPU or GPU or whatever your proof of work scheme is working on and strip away everything you don't need. So well, still it can be very differently complicated on to create an ASIC, and this is something I want to shine on. First of all, it's of course the benefit of your ASIC over the common hardware. If your proof of work scheme is able to utilize one particular aspect of your hardware very, very well, then it will be very complicated to create an ASIC that's able to outbeat that, unless it has a lot of more capacities into exactly that direction. So, and of course, this is also a selling point. The higher the benefit an ASIC has, the higher the vendors can put the price, and the better they can do their risk management when trying to create such a thing. Second aspect is the development effort. If you've got a proof of work scheme that's very complicated and where a design is very hard to validate if it's creating correct results, that will lengthen the time to create an ASIC extremely. Let's take, for example, RandomX, what Monero uses. The algorithm is such complicated, and yeah, that I don't believe it's impossible to create an ASIC, but it would be horribly expensive in aspect of time for the designers to make one. Then, of course, the chip size. There are proof of work schemes, let's take Cookatoo for example, that are rather ASIC friendly. In terms of the benefit of ASICs over the common hardware would be huge, and the design is simple, but the chips created there are so big that it gives very bad yield rates, and it's pretty hard to create these things with reasonable costs. So an ASIC in this case would be horribly expensive, and so you first of all need to find enough people that are willing to buy these things. Then, last but not least, the stability of the proof of work scheme. If your government of your coin project says, okay, well, if an ASIC is coming, we run away and fork for a new scheme, well, then the ASIC is worthless before it was even created. So, well, and this is the only aspect where you can maintain real ASIC resistancy by forking away very often and change your proof of work scheme whenever you believe ASICs are out there. So, by the way, it's not only that there are multiple aspects behind ASIC friendliness, it's also that there's not in particular one type of ASIC, but well, we can kind of group them into two different groups. So one group is the commonly known single chip ASICs. That are the type of ASICs, well, you believe to get a single monolithic chip that is built for the single purpose of just running this one algorithm. And well, they have the advantage that they are often much quicker than any GPU or CPU running, and also quicker than the other ASICs I'm going to present in a few seconds. But especially for complicated algorithms or those which need a lot of memory, they have a much larger chip size. Well, the other type of ASICs are multi-chip ASICs. That are rather rare things. The only ones I really know are those for Equihash, where you have multiple chips mixed with distinguished functions. And for example, for the Equihash ASICs, those are memory chips combined with a small compute chip that does the actual hashing then, but with external memory aside. those constructions can be built much cheaper because the chips are smaller, you got better yield rates in production, and also the design is often less complicated. The only downside is they are not as fast as single chip ASICs, especially when the bandwidth between the chips is an issue or a bottleneck. So I got asked a lot, okay, what exactly is the strategy of Beam for proof of work? Why don't you change the proof of work every 6 months? Well, there are multiple things behind that, and one, of course, is we want to avoid the disruption of the mining ecosystem. We have seen that sometimes for other projects that when the proof of work scheme is changed, we see some mining software not getting updated, some pools not updated in time. Well, we have taken a lot of care about this in the past, and we will do for BeamHash 3. But still, every time a fork happens, there are some miners left behind that do not care about their rigs or don't monitor them too often and don't update them. But also, well, sometimes you just lose parts of your mining ecosystem when forking. The other thing is mining is important, but even I have to admit it is not everything. In fact, miners are important because they are the first believers of your project and the first people who handle your coins on a certain scale. But on the other hand, when your project fails to get behind this mining community, well, they're also the last believers, and often the project fails overall. So the next aspect is more important for us, and this is mass adoption. Similar to the disruption of the mining ecosystem, it is a problem. It is a problem for mass adoption if your consensus changes too often. If you want your coin to be used everywhere, you must make sure that even a client that's 2 or 3 years old still works, and without having the users to permanently maintain their nodes and everything around. This is why we have all those big consensus changes now put into the beginning of the development phase of Beam, and have nothing on the roadmap that's very, very far ahead that will break the consensus again. The only thing that is left after the next fork, that is Ghost Deck, that we'll research afterwards. And it's likely that this will be one of the very last consensus upgrades we do with Beam in order to provide optimal stability to make it usable. This doesn't mean the development completely stops. The wallet can still be improved. Everything around can be improved. Adoption can be improved. There's way enough headroom left. So our strategy, we give GPU miners a head start. Our proof of work schemes are created in a way that they run very well now on GPUs and also for the next years on GPU. Now, when the rewards are high, this coin is mineable best on a GPU. So they get the big piece of the cake. Then we want to make mining as relaxing as possible. I already mentioned we did put a lot of effort into having good contact with other miner developers, with the pools and so on, to allow features like the auto switch from BeamHash 1 to BeamHash 2, and what we'd like to have again for BeamHash 2 to BeamHash 3. So the miners don't have to care about what's going on when the fork happens. Their rigs will just adjust to the new method and everything will be fine. Well, this is one aspect of making it relaxing. The second one is, of course, we want a proof of work scheme that's nice to mine. For example, by making it a little bit more lightweight in computing, so having a low energy use, and this allows us to spread out mining also into areas of the world with higher energy prices. Well, and the last thing is, when the first ASICs will come, we try to make them cheap. So you will see later BeamHash 3 is designed in a way that will hopefully allow some cheaper designs in the beginning, most likely not single chip designs but multi-chip ones. So if ASICs come earlier than we expected, they're likely cheap enough and affordable enough, so we can have a certain adoption in our mining community for these devices. So I'd like to give a short introduction about how Equihash works behind the scenes, so you get an idea what we did change and why for BeamHash 3. The first part of this is the seeding. Seeding means the very beginning phase when we fill the memory of our GPU with kind of random data or pseudo-random data. And in every Equihash, it's more or less done the same way. We have incoming word as work, nonce, and an index, and put that into the Blake2B hash function. Afterwards, from the result of Blake2B, we generate a bit string that belongs to a certain index. So what iterates is the index, while the work and the nonce are kind of constant. And by doing this, we fill our complete memory, around 2 GB in this case, with random data. When the seeding is done, the next phase is the matching phase. Matching means we sort the elements in our memory by their least significant bits. Here, for example, this 1100, and search for elements whose least significant bits are matching. So what we do then is we apply the exclusive OR operator and generate new elements, output elements that are 0 on these least significant bits. For BeamHash 1 and 2, this is done on 25 matching bits. So, well, here in my graphics it's a little bit short, just because 25 bits doesn't fill my screen well. So this is done in every round. So in the beginning we had full bit strings. After round 1 we have shorter ones that lack 25 bits. After round 2 even more bits get lost, and so on and so on. In total we do this 3 times with our complete data set. The number of bit strings in our memory is balanced in a way that for each round the amount of in and outputs are approximately of the same size. So we kick off with 2 to the power of 26 elements and come out with approximately 2 to the power of 26 elements for each round. So of course some elements don't get matched, some get 1 times matched, but others get 2 or 3 times matched. And that amplifies enough to keep the total number of elements approximately constant from round to round. So while doing so, going from round to round, we at the same time grow a kind of index tree. It starts out that we match 2 elements indexed by A and B and combine them to one that has index tree AB. Then we see, okay, can this be matched again? And if we had a match of D and C, then that has the same kind of output on the least significant bits that are then needed in round 2, we can match A, B together with DC to create ABDC. You may wonder, why is this guy mentioning D before C? Well, this is to make a point that the order of elements actually matters. The index tree is always built in a form that the lower index comes first. So in our case, if D was just less than C, then D comes first. But then if A is less than D, we put AB before DC. The rule is, when two blocks match, then we have a look to the lowest index in each block and order the blocks depending on this least entry. So I already mentioned we match 25 bits for BeamHash 1 and 2, and well, 50 in the last. The reason for this is to reduce the number of outputs. This 50 gives us exactly 2 solutions on average for each iteration. On average, we can be lucky and have 3, 4, or 5 solutions, but sometimes we also can have bad luck and have 0 or only 1 solution. This is a little bit the reason why Equihash servers are always a bit wavy in their speed, because the number of solutions found per iteration is not constant, but the speed per iteration is kind of constant, so you always go a little bit up and down with your speed. Well, and we do this 5 times, so if the index tree size doubles every time, you see every valid solution in the end has 32 indices that give an XOR of 0. This was a slide that was kind of hard to write. Well, why? Because I obviously like Equihash, but still we thought, okay, when we upgrade our proof of work, we still could think, okay, what could we do better? And so I needed to brainstorm a little bit what some of the Equihash issues are. First, to mention some implementation aspects. The most annoying one is the number of bits we move around through the memory changes every round. This is something that makes the implementation quite complicated, because for every single round you need a more or less optimized code. Yeah? Your bit strings get shorter and shorter, and you try to optimize somehow for these shorter writings and shorter readings in order to utilize your memory very well. So this makes the implementation quite clumsy. Additionally, the index tree is kind of scattered. You don't have it nicely in one place, but you always try to, well, if I just know, okay, this element was generated from 2 ancestors, then you store this information somewhere aside and proceed with the element just by knowing, okay, exactly there is my element backtrace stored. This allows to save memory. As said, minor developers tend to optimize everything, so you kind of reduce the number of bits you read and write there. But this makes the reconstruction of the index tree quite complicated afterwards. Well, and you need a quite massive filtering of invalids midway. Consider the situation that the same element takes 2 different passes through the index tree, and then sometimes an element is getting matched to itself. Okay, obviously that XORs to 0. And sometimes you have the strange situation that by this way you generate whole families of elements that are kind of have some kind of inbreeding here. Yeah, and that fill up your buffer with intermediate results that would never give any valid solution. That may sound a little bit exotic, and unlikely, but in fact that happens much more often than you would think of. And especially from round 3 or 4, you really need to filter out such invalid solutions. So beside this, there are also some algorithmic aspects that could be better of Equihash. For example, Blake2B, the way we fill our memory in the beginning is very compute heavy, and this requires us to have a quite high clock core on our GPU. And well, this is something you don't necessarily like because it requires high energy consumption, but else if you clock the GPU lower, you end up with lesser speed, so this makes the tuning on the graphic card less nice. Another aspect is the elements that we store and load are rather small. This is in particular a problem for the GPU architectures. They are often made to read and write large sequential batches of elements, but here we need to sort stuff short as 128 bits or 150 bits into buckets to match the elements afterwards. So, and this is something that works well on some architectures, in particular NVIDIA graphic cards, but in others it doesn't. And well, this is not optimal for a coin that wants to be well GPU mineable, because any special device that is optimized for this small elements, loads and store into a common memory could have a bit benefit from being able to do this particular task very well. So we wanted to get rid of the very small elements here. So finally, some time for the BeamHash 3 basics. I'm now going to show you what we did change and why we believe this can help us improve the situations I just mentioned. So we start off with the seeding. In the seeding, we now only take the work and the nonce and put that into Blake2B. You see, okay, this happens exactly once for every iteration. Then we took in the index of our element we want to generate and use ziphash to create the element, the bit string for our index. This has the advantage that ziphash 2.4 is much simpler to compute than Blake2B, and so those part of the algorithm that's done in mass is much more compute lightweight. Special thanks here to the guys at Grin. This is kind of borrowed from the Cuckoo family, where we have a kind of initialization and seeding phase that follows a similar pattern. Additionally, we also changed the round code by introducing a mixing function before any bucket sort or matching actually happens. So when we just created an element, by matching, we take its new values plus its index tree, the index tree in full in the right order, and apply it to a mixing function that mixes around the lowest 64 bits of an element. So especially those bits that are now relevant for the next matching get changed. By doing so, we kind of force the miner to always keep track of the full index tree, and also to keep track of all of the bits that were there in our element before the bucket sort. Before, it was possible to only take a fraction of the element, match it, and afterwards, once matched, load those values we had before and put it together afterwards. This is now no longer possible, Instead, we always need to take the full bit string plus the index tree and keeping them all together all of the time. So this is some of the most important basic properties of our new BeamHash 3 from implementation side, because we start with this much longer elements, 448 bits. And well, these extra bits we have there, we don't match them all. We now only match on 24 bits, but we reduce the number of extra bits in every round, so the total bit length we need to handle plus index tree both together fit into 64 bytes, so 512 bits. This is much better suited for GPU load and storage operations than the stock Equihash. Secondly, since the index tree, as I mentioned, is part of the mix, it does make sense to keep it kind of scattered, and that overall ends up in a very simple memory layout. In fact, the reference miner only has two memory buffers, one that's input for a round and one that's output, and in the next one they just can swap. They always have the same size and kind of the same access structure all over the 5 rounds that happen. Well, and the likelihood of inbreeding is much reduced, and the new proof of work scheme in fact can work well enough without filtering the invalids midway. So arithmetically, I already said the generation of elements, the seeding is much less compute heavy. Additionally, H, load and store is 64 bytes, which hits the level 2 cache architecture of current state-of-the-art GPUs very well, and should overall allow us to much better utilize the memory bandwidth a GPU has. Well, so my conclusion about BeamHash 3, first of all, it's much easier to implement than BeamHash 1 and 2. Just check out the reference miners. It fits very well into 5 GB of memory. That's a simple memory layout. 4 GB are well possible and rather easy to achieve. 3 GB are theoretically possible. If we will see, 3G minus depends a little bit on what the mining software developers are willing to implement. Well, it is made to utilize the memory bandwidth of our current GPUs better than Equihash did, and it will be single chip ASIC resistant for the next years, just because the required memory of BeamHash 3, even when you do a very minimalistic implementation, will need at least 2.5 GB. You almost can't get below that. And this is something you cannot make with current 7 nanometers process, and it's also unlikely that the new TSMC 5 nanometer can do that. We will need to wait at least 1 or 2 more generations of factoring process for chips. Well, and in case anyone wants to do a multi-chip ASIC design, then the compute chip in there can be very small, very simple. All you need is a small compute chip accompanied by a lot of memory. So we hope, in case we see ASICs earlier than we expect, because they're multi-chip ASICs, then they hopefully will be more affordable for the mining community. And so, finally, we believe BeamHash 3 is a good proof of work for Beam to go with in the next years. Wow, I can't believe you're still here. Well, but I'm quite happy, and I thank you very much for your attention. If you got any questions to this, feel free to ask me, or in a few days I'll have an interview about the new proof of work scheme with our community manager Rascal, and you'll be able to submit questions for this Q&A session we want to do. Look in the description below for details where to submit. Thank you very much. See you soon.